All right. Good morning. We are going to start today with Unit 1. This is Computer Science Principles, Unit 1, Digital Information, Lesson 4, Binary Numbers. This is one of my favorite topics to go over. In this lesson, we're going to cover standards, CSP conceptual frameworks, DAT1. The way that the computer represents data is different from the way that the data is interpreted and displayed for the user. Programs are used to translate data into a representation that is more easily understood by people. And standards CSTA K-12 Computer Science Standards 2017. This is DA Data Analysis 3A-DA-09, and that is translate between different bit representations of real-world phenomena such as characters, numbers, and images. So today for our warm-up activity, yesterday or the last lesson, whenever that was, we created our own number system using circles and squares. Today we are going to discuss what can we communicate using only two symbols, and is there a limit? So if we take a look at our, let's see, I'm trying to see if there is an interactive notebook that we can document this in for our discussion today. But let's just start off today by thinking of those ideas, pairing up with a partner, and then sharing our thoughts as a class. Goal of this, just write down your answer, and then we'll go through those different group levels and discuss it. Discussion goals for this is, in previous lessons, students represented information using two options. This is a quick thinking question to tap into students' prior knowledge and experiences. Once students have mentioned a few of the points below, then you can move on. So teachers, take a look at your lesson plans in the teaching guide and see if there are any of those things that they are mentioning. Go ahead and pause the video, and then we'll go over those four or five things that we want the students to get. So go ahead and pause the video, individually write down your answer to the discussion question, pair up, and then discuss as a whole class. All right, now that we have discussed that as a whole class, things that we were looking for, or potential things that we were looking for, if we haven't gotten there, pause the video, and then we'll get to those answers. But the answer to a yes or no question or a true and false question would be things that we're looking for: flipping a switch on or off, combinations of yes/no answers by using multiple symbols in a row, and then can we keep adding more of the same symbols so the only limit is how much space we have to write or store those symbols. Those are some of the things that we're looking for. All right. For our activity today, you and your partner should each have a pen or a pencil. And if we take a look, just want to make sure that we are getting the correct activity guide. All right. Use the activity slides for this lesson to introduce students to the binary number system. Use the presenter notes as a guide to explaining how the shapes we used in the previous lesson relate to binary numbers. These slides use a lot of animations. Look for this symbol on the slides to show, so it's going to be like a little 3-dot symbol, but you can follow along with what we're doing here. So we're going to go through this. All right. With only one place value, we only have two possible patterns: a circle or a square. So we started with a circle, but we could have easily started with the square instead. Now we have two place values. So we've got our circle or we've got our square. Okay. And then now we have four possible patterns. So with two place values, we can make two sets of the previous patterns, then insert circles in front of the first set and squares in front of the second set, and this makes four possible patterns: 1, 2, 3, and 4. For three place value patterns, we can make two copies of the two place value patterns, then just like we did before, fill in the first set with circles in front of the second set with squares in front. This makes 8 different arrangements. computer scientists like specifically counting at 0, but it's whatever your preference would be. I would say that we should start at 0 just because for this specific lesson it just is going to work out, especially when coding with binary earlier on, and we'll explain what this means or what this looks like. Okay. Instead of 2 shapes, what if we had 10? So in place value, 10 is equal to 1 of the shape patterns. So we could use more geometric shapes or we could use letters, but the shapes we are used to are the numbers 0 through 9. Okay, so if we were to represent those as shapes, this is how this would look. With 2 place values, we have 102 shape patterns, and these are just numbers 0, 0 through 9, 9. Okay? So, what happens when we count up to the last shape, or last digit? What happens once we get here? Okay, so once we get to this, we have to add another placeholder, because here's our 3 placeholders. And now once we get to here, obviously, next thing is going to be 100. When we run to the last shape of 9, we roll over back to 0 and add 1 into the next place to the left. This is the place value that we have used for all of our lives, correct? So where are we heading with this? To binary, okay? Binary is a number system with 2 shapes. It's going to be 2 shapes like this, 2 shapes like this, but typically binary is going to look like this, 0 and 1. For today's activity, we're going to be, instead of shapes, we use 0s and 1s, so that in this example, each pattern maps to a decimal number from 0 to 7. So here's 0, 0, 1, 2, 3, 4, 5, 6, and 7. Right? So, for today's activity, you're going to be creating your own Flippy-Do. This is a tool that will allow you to quickly and easily translate between a decimal number base that we are used to as humans and the binary number base that computers use. So, teachers, I would like you to hand out the Flippy-Do templates, 1 per student. It's going to be this here. Okay, so print these out if you haven't yet. Hand them out one for each student, excuse me. And then we're going to complete your Flippy-Do using this slide as a guide. So we want it to look like this. We want to put in the powers of 2. Okay, so 2 to the 7th, 2 to the 6th, all the way down to 2 to the 0. Write in the whole number equivalents. Okay, so 128, 64, 32, 16, 8, 4, 2, and 1. So that looks like 728 in my opinion, but it's a 1. And then write a row of zeros. And then we're going to flip up the bottom sheet and we're going to write 1s on the bottom. And then we want to cut along the dotted lines. Okay? So you need to replicate this, making sure that we don't have 1 on the bottom side, but we flip it up first and then put the 1 on the bottom side of the dotted line, so that way it's either showing 0 or if we flip it up it'll show a 1. And then cut along those dotted lines. So make your Flippy-Do. If you don't have that made yet, then pause the video and we will come back. Alright, so now that we've got our Flippy-Do made, we're going to try out the 6 problems. So each place value represents 1 bit or binary digit. The bit can be a 0 or a 1. So your Flippy-Do obviously has the 8 bits, which together will make 1 byte. 8 bits make a byte. So trying out our Flippy-Do, represent these decimal numbers in binary. Okay, so if we take a look at our Flippy-Do, let me get my sheet out here quick. Okay, so what we're going to do is we've got our our 8 placeholders are zeros, okay? And working from the right to the left, we want to represent our binary digit. So the first one is 0. Let's go back to our flippy-do. We want to represent 7. Okay, so the easiest way to do this is working left to right. So if I start at 128, 7 can't go into that. It can't go into 64. So I'm placing zeros or leaving zeros down on all those. Can't go into 64 because I want to represent 7. Okay, so 0, 0, can't go into 32, can't go into 16, can't go into 8. It can go into 4, so I'm going to place a 1 there, and now I'm going to take 7 and I'm going to subtract out 4. So what am I left with? I'm left with 3. Can 2 go into 3? Yes, it can. So I'm going to put a 1 in that placeholder, and then I'm going to subtract 2 off of 3. Now I've got 1 left. Can 1 go into 1? Yes, it can. So I'm going to flip that one up, and now I've got a 1 there. So in binary, how 7 is translated is 0, 0, 0, 0, 0, 1, 1, 1. Okay? So that's how 7 is represented. Our next one was 20. So how am I going to represent 20? Again, we start at our 128 place. 20 cannot go into 128. 20 cannot go into 64 or 32. So I've got 3 zeros to start us off. Can 16 go into 20? Yes, it can. So I place a 1 there in that placeholder spot. I subtract 16 from 20, and I'm left with 4. Can 8 go into 4? It cannot. Can 4 go into 4? It can. I place a 1 there. So I should have 3 zeros, a 1, a 0, a 1, but I can't forget my other digits, otherwise this binary representation is going to be all off. So I take 4 away from 4, I'm left with 0, and so I'm going to finish out my binary digit with 2 more zeros. So 20 should be represented as 0, 0, 0, 1, 0, 1, 0, 0. Okay, so that's 20. Let's go to our sheet here quick. Now represent these binary numbers in decimal. So I've got 0, 0, 0. So if I write out on your flippy-do, you've got 128, 64, 32, 16, 8, 4, 2, and 1. Okay? If I look at these numbers, I've got 128 here in this zeros place, 64 in this one, 32, 16. This is a 1, so I've got at least 16 plus not plus 8, not plus 4, plus 2, and not plus 1. So I've got 16 in this placeholder, plus 2. So this representation here is 18. Okay? So that's 18. Starting over again, I have a 0 in the 128's place, a 0 in the 64 place, a 0 in the 32 place. I have a 1 in the 16's place. I have a 1 in the 8's place. I have a 1 in the 4's place, a 1 in the 2's place, and a 1 in the 1's place. So I have 16 plus 8 plus 4 plus 2 plus 1. So I have, let's do some quick math here, 10, 31, right? 10 plus 20 is 30 plus 1, yes. So that would be 31. So this binary number here in decimal is 31. Okay? All right. There we're seeing our representation of this. 18 and 31, we did those correct. Beautiful. So now we're going to go to our flippy-do activity. So as we go on here, use your flippy-do to help answer these questions. All 4-bit numbers, fill in the binary equivalents for the decimal numbers below. We've started the first 3 for you. Okay, so binary 4-bit, and we're looking for our decimal numbers. So we've got 0, 1, 2, I want 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so 0 to 15. Okay, teachers, if you need to, you can pull up the lesson plans for this, and then you can pull up the flippy-do activity guide key if you need to. so that way you've got it. But we're looking for 3 through 15 here for our decimals, and then we want the binary 4-bit number representation. Okay, so what do you notice when you compare the odd numbers with the even numbers? What might explain this? So taking a look at those, see what you're noticing. Okay, pause the video if you want to, but then we're going to have a quick little discussion about this as a class. So one thing that I notice is that all of the odd numbers in binary seem to end with a 1 in the binary. So I've got my 0001 is ending with a 1. If I were to represent 3, it would be 0011, again ending in 1. If I would do 5, it would be 0101. So the odds seem to end in 1. Even numbers always end in 0. This is because the 0 position is the only position with an odd value. The rest of the positions are multiples of 2. The only way to get an odd value is to include the ones place, which is in the position of 0. Okay, so we can put something along those lines in this space here. Put a couple sentences, 2, 3, 4 sentences in there explaining that. Next, we've got binary numbers with exactly 1, 1. Complete the chart with all 8-bit binary numbers that have exactly 1, 1. We've done this first for you, or the first two for you. So we've got 1, 1 in here, so I should have 7 zeros and 1, 1. Okay, so we should have our binary representation of that. Go ahead and pause the video, take a look at that. We can do the one here, or the next one here as a team. So I've got the 128's place, the 64's place, the 32's place, the 16's place, and then what is this? This is the, this is the 8's place and then the 4's place. So this decimal representation here would be 4. Okay? So pause the video, work through those. You should have 7 zeros and 1, 1 in the column that says binary 8-bit number. What do you notice about the decimal equivalents above? They are all powers of 2. Values double each time, right? So as we work through that, we should see 1, 2, 4, 8, 16, 32, 64, and 128 in our decimals column, and then I will let you do the binary equivalent of what that looks like. All right, conversion practice. So now we need to convert the binary or the decimal vice versa. Okay, so use your Flippy-Do charts here. If you have any questions, you can reach out to your teacher. Hint here, especially at the ends of these two here, we might have more than 8 bits. You'll have more than 8 bits. So make sure that as we're going through that you leave enough space so that you have enough bits in there. If you need help with those, ask your teacher. Teachers, you can go ahead and open up your Flippy-Do. You can open up your key if you need help with that. Okay, and then these discussion questions, I think that we should go through as a class. So when you add a 0 to the right of a decimal number, it multiplies its value by 10. For example, 15 becomes 150. What similar result happens to the value of a binary number when you add a 0 to the right? For example, if I go from 1, 1 would become 1, 1, 0. And if we do that, the value is multiplied by 2, or it is doubled. Each position must shift to the left to make room for the extra 0, and this causes all the values to be multiplied by 2. All of them, not just the 1. Okay, so if I had 1, 1, that would be 3. If I had 1, 1, 0, I would have 6, right? Because I have a 1 in the 4's place, a 1 in the 2's place, and a 0 in the 1's place. 4 plus 2 is 6. And before I had a 1, 1. Okay? So we're getting, it's being multiplied by 2 or doubled each time. Each position that we shift to the left if we add the 0 to on the end. So put a version of that comment in this space here. Do the binary numbers 0011 and 000011 have the same value or different values? Explain. The value of this doesn't change because the zeros that we added on the left side are going to be they're not going to have any value. There's zeros in those placeholder spots, so there's nothing being added onto the value. So the original bits do not shift. We are including more bits in our number, but the value of each bit is 0, so the total value is not affected when we add 0. Okay, so any of those zeros on the left side aren't going to change the value. Would 2 bits be enough to assign a unique binary number to each vowel in the English language? Explain. Okay, if we have 2 bits, so we only have a 1 and a 1, how much in decimal value do we have to work with? Well, if we have a 1 in the 1's place and a 1 in the 2's place, we only have a 3, right? 1, 1 represented in binary is 3. So since there are 5 vowels in the English language, we would actually need 3 bits to represent all of the vowels in the English language. A, E, I, O, U, right? So we'd need 3 bits in order to represent all 5 vowels in the English language. And our last question, how many bits would you need if you wanted to count up to the decimal number 1,000? Okay, so this, we've got 1,023. So if we take a look at our current binary, whoops, excuse me. If we take a look at our current binary or some of the stuff that we've looked up at the top here, so when we were working on this 513, that's going to require how many bits for us to do? So I've got, let's work through this problem. So I need to double up to, after 128, because I've got 1, 2, 4, 8, 16, 32, 64, 128. Even if I added all of those numbers together, I would only have 255. Okay, so we start with 255, and that's 8 bits that we're doing. 255 is going to equal 8 bits represented. What is the last digit value worth? It's 128, correct? 128 plus 128 is what? 128 times 2 is 256. Or one more than all of the values of the 1 digits in our 8-bit binary. Because all of the 1s are 255, all 1s, 255. I add 1 to that, that's what my next double is going to be. So 256 is going to be my next placeholder, and that's at 9 bits. So if I had 1 with 8 zeros after it, that's going to be 256. There's our answer for this one. 1 with 8 zeros after it. So I've got 9 bits. So 256 doubled, or 256, sorry, plus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is what? Well, if I take 256 times 2 is 512, that's what that's going to be, right? 512, right? Or sorry, 511. Let's do the math quick. Calculator. So I've got a 1 with 8 zeros after that. That's 256 with 9 bits. 256 plus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. 511. Okay? So 511 is 9 ones in binary all in a row. If I want to add a 10th bit, because we're trying to get to 1,000, I want to count up to 1,000. Okay, so I'm at 511 with 9 bits, and they're all 1, so I'm out of room. So I need to add on another bit. And that 1 followed by 9 zeros, so 1 in the 10's place, or in the 10th bit, and all zeros after that, 9 bits after that, is going to equal 512. So 512 is a 1 with 9 zeros after it. Okay, so I know 512 is that 10th bit value. Now I'm going to add, and I'm going to see what this 10-bit value maxes out at. 512 plus 256 plus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. There is an easier way to do this, but I'm just doing it for the sake of showing you what all those place values are again, so that way it helps. 1023. So we could, in a 10-bit representation, show 1,000, right? Because I've got 1,023 to work with 10 bits. Now, if I wanted to make that simpler, I could just take 2, if I go to my scientific calculator, if I take 2 to the power of whatever I want. Okay, I'm curious if I can do it here. That's square roots. 2, where's my caret symbol? Oh, there we go. 2 to the power of 8. There's 256. If I do 2 to the power of 9, 512, right? Because remember, they're 2 to the base of 2 to the power of 10. 10 bits. 1024. So there's an easier way of getting to it. We chose the harder way because I wanted to try and drill in the bit value representation of all of those placeholders, so that way we work through that. But if we wanted to just quickly get there to see, okay, I've got 5,000 is my number, or 7,500 is my number. Let's say 7,500 is my number. If I take 2 to the, I have to get up to 7,000. Let's see if I need 12 bits. Okay, so 2 to the 12th is 4,096. 12 bits is not going to represent 7,500 for me. So 2 to the 14 maybe. 6, so we get exponential very quickly. So I didn't need to jump up to 14, so let's see what 13 gets us. 2 to the 13th. 8,192. Okay, so if I wanted to represent 7,500, I would need 13 bits. Okay, so take 2 to the power of, you kind of have to extend your flippy-do chart if you wanted to, but hopefully that helps us get there. Hopefully that helps us understand how that all works. Okay, so we'd need 10 bits to allow us to count to 1,023, since the 11th bit has a value of 1,024. Okay, so that's what we would put there. Let's get down to our next thing. So we're going to check for understanding. So our peer instruction, each time we add another bit, what happens to the amount of numbers that we can make? Question would be, 2 schools are merging, and to adapt to the increased size of the student body, the school is changing its system to keeping track of all students' IDs from a system that uses 4-bit binary numbers to one that uses 8-bit binary numbers, aka 1 byte. Which of the following best describes what effects this change will have? So that's what you should do in your check for understanding on code.org. Okay, I think if we want to, for our interactive journal in our notebook, we're going to cut out these vocabulary words on the left and paste them in our notebook. So binary number, bit, and byte. And then we want to add definitions, images, and representations that are unique and meaningful to you. So after going through our lesson today, write down your definition of what those things would mean, or what they are to you. Remember, binary is a way of representing information using only 2 options. A bit is a contraction of a binary digit, the single unit of information in a computer typically represented by 0 or 1, and then a byte is going to be 8 bits. A byte is 8 bits. So that's what we need to do for our interactive notebook, Unit 1, Lesson 4. And then in our journal, use this page to add vocab words throughout the unit. Design each vocabulary canvas with definitions, images, representations that are unique and meaningful to you. As an understanding grows through the unit, you should be able to have a canvas, and you can always come back here and add in more things. So we're going to start with binary number, and then we've got bit and byte. I think that's it for those two. So we're just going to add those in, and then maybe at the end of the unit, we'll take this vocabulary canvas and we can cut these out, or create a journal that's got several vocab items in there that we can make into a vocabulary canvas. That's what we're doing with our interactive notebooks. Each student should go into code.org and do their check for understanding Flippy-Do assessments on there. And then for our wrap up, it's important to know the differences between binary and decimal numbers. As a review, the decimal number system is base 10. These are 10 different symbols used to represent numbers 0 through 9. The binary number system is base 2. There are 2 different symbols used to represent numbers 0 through 1. Using our Flippy-Do, we can convert between binary and decimal number systems. While it is easier for humans to use the decimal number system in our everyday lives, we will see later in this unit how electrical signals inside computers can be best represented by using the binary number system. Okay. Some things to talk about, teachers, is number bases and why binary. So students will see in a later lesson how computers use binaries. Binary numbers is a representation for electrical signals on a wire. The wire is always set to one of the 2 different options, on or off, and represented by a 0 or a 1. So it's just how computers compute with electrical signals, and that's why computers use binary. Some teachers, again, in your lesson plan, there's some options or some details that are in there in order to help students have examples of what they might want to put on their vocabulary canvases, which is what we've got here. So make sure that students have time to add those vocabulary words to their journals. And then for our assessment check for understanding, again in code.org, now we're at number 3 and 4, checking for understanding. 2 questions that you should be going through are how many bits would be needed to count all of the students in class today? And then what are the similarities and differences between the binary and decimal number systems? So as we go through that, answer those 2 questions. If you have questions for your teacher, make sure you ask them, make sure you get through your vocabulary canvas, and then make sure you get through your check for understanding questions. Complete your activity guides, make sure that you hand those in, your Flippy-Do charts, your journals and your lessons, and that should be the end of, let's just double check. Dun, dun, dun. There's some examples of vocabulary canvas. What else could we add in there? There's some links on here, some acronyms. Could link in other words, represent them, conceptual map and draw them between each other. So byte and bits and how they are interlinked. And then, so yeah, teachers, you can go through those slides in Unit 1, Lesson 4 to help students make sure that they get their vocabulary canvas created and their visual representations, words, initial definitions, things like that, all in there. But that is the end of Unit 1, Lesson 4. Binary numbers, I'm pretty sure is what this lesson was called. Yep, binary numbers.